So our next presenter is Dr. Illias Papadopoulos. I hope I pronounced that correctly. He is a research fellow in the Engineering Seismology at the University of the West Indies Seismic Research Unit. A lot of us are excited to listen to your presentation titled Trinidad and Tobago Microzonation Project, the case study of Port of Spain. So please welcome.
Hi, good morning, everyone. As mentioned, my name is Ilias. I am the engineering seismologist at the Seismic Research Center in UE since 2016. And I'm very happy to be presenting things to engineers. I'm very nervous when I'm around engineers because you are very smart people. And I kind of feel like, I don't know. Anyway. The reason why I decided to show you Port of Spain, we have done microzonation studies in several islands in the Caribbean. I have worked microzonation studies in 4 different continents. The reason why I chose Port of Spain in particular is because we consider it now a complete study. So today I'm going to show you the microzonation, which is the seismic hazard of the area, and tomorrow I'm going to show you the risk assessment that we did for the same area. Okay? So I hope that you will enjoy the presentation. I'm pressing the 2 arrows to go back and forward. Right, okay, let's see how this. So the project itself is a 15-year project between us and the Ministry of Planning and Development in Trinidad. The idea was to microzone 9 urban areas. We are so far reached 6 that we have already collected the data and we're processing them. And the deliverables will be to provide the resonance frequency of the soil above bedrock, to provide amplitude of the waves, hopefully to reach to amplification of waves, and to identify seismic vulnerable areas within the urban areas that we are studying. All right. As Mr. Gibbs showed you, the seismic hazards that we have produced back in 2011, when we want to define the seismic hazard, we have 2 ways nowadays to do it. One is the statistical approach, which is the probabilistic hazard assessment, the PSHA that Mr. Gibbs showed you earlier. And the second one is to do an actual measurement of the amplification. That can be done in 2 ways. One is by installing seismometers in areas and then actually record earthquakes, which has the advantage that you do record the earthquake, but the disadvantage that you have to wait for a very long time, especially in moderate seismicity areas as is the Caribbean. That will take very long time. The other option we have is to do a microzonation. So microzonation is to actually using passive seismic noise, not earthquakes. Record that, and from there, try to extract as many information as possible. All right, so how it works. Assuming that we have a fault plane somewhere deep in the ground, and we are having the generation of an earthquake. The seismic waves are going to travel, which we call it the path, and then they are going to reach the surface, which is what we are going to record. Now, the part of the travel that is going to affect greatly how the waves are going to reach the surface is what we call the local site effects. So it is the few dozens or hundreds of meters below us that it is the sediments above the seismic bedrock. As you can see on the image, if I was to collect the waveform at the bedrock and collect it at the surface, you will see that you will have an amplification when it will reach the surface, and it's being recorded by the instrument. Now, to make it a little bit more engineering, let's assume that we have a 2-layer case. We have the bedrock, and above it we have sediments. So the wave, as it's going to be recorded at the surface between the bedrock and the sediments, it will be the A0. And then when it reaches the surface, it will be the A1. So what we need to define is what we call the transfer function that transforms the A0 to A1. Now, this function, we usually tend to consider the soil as a 1 degree of freedom oscillator, that it's being moved by the seismic energy. And from there, if we are doing a spectral analysis, we can, in simple cases, we can actually find the resonance frequency of the soil. Now, you as engineers know how important it is because you also need to find the resonance frequency of your buildings, which you also consider, in the simple cases, a single degree of freedom. Now, the generation of the seismic noise can be done in different ways. It can be atmospheric, so we have rain, we have waves. It can be human-made, so traffic, generators, trucks, pedestrians, whatever can people make to create some noise. And all of this altogether is recorded as what we are calling the passive seismic noise. Now, coming to how we do it, you see the map of the Port of Spain. So we created a grid of measurements. Each measurement was 15 minutes long. So effectively, we went everywhere in town. And then we are doing, I will show you the results of the whole thing. So what we are doing is what is called an horizontal to vertical spectral ratio. So we take the horizontal components, and then we divide them by the vertical. And this is going to give us, in the simple cases, a single peak. That peak defines the resonance frequency of the soil above bedrock. Now, this method, when it was first introduced, we were hoping that it will also give us the amplification. But unfortunately, the amplitude that we record with the passive noise is not coinciding with the amplitude, with the amplification of the soil over seismic excitation. Now, the second method we are doing is called an array measurement. So we have more than one instrument in a setting. And as the seismic noise is passing, we record it in the different sensors. And from there, we can get the 1D velocity distribution over depth. Now, this is helpful for us because we can actually create a geological model, a 3D geological model, where we can actually know how deep is the bedrock. It is very useful for us to have a model like this. Now, you all know this one, the NERP classification. So we also provided a map of the city that classifies it through the 5 different categories of the hazardous NERP. So to get to the NERP classification, we have the single measurements that we are doing. We're having the geological survey of the area, and then we are producing synthetic models to simulate the noise that we have collected, and all of them combined together, it will give us the NERP classification. So this is the recordings that we did inside the city. It was more than 1,000 recordings at about 100-meter sampling. And this is the fundamental frequency map that we produced for the area. The fundamental frequency usually correlates with the depth, or the thickness of the sediments, or the depth of the bedrock. While in the next slide, we have the fundamental period, which correlates better with the shear waves velocity of the sediments. Now, on the next one, we have the sites where we actually did the 1D velocity profile, which when we integrate it, it will bring us to this side. So this is interpolation of only the sites that we actually measure the 1D velocity profile. And then on the next one, we have the integration of all the available measurements to show us what is the geological model of Port of Spain. So as you can see, ranging from the hills, can you please go back one? Ranging from the hills to the sea, it is an alluvium fan where we have the gradual deepening to the bedrock at the coast close to 150 meters. The next one is a assessment. I need to be very careful how I'm going to phrase that. This is an assessment of vulnerability, meaning within the same area, comparative, if we all live in Port of Spain, which areas, when the earthquake is going to happen, which areas the ground is going to be more vulnerable or not. All right. This one was first introduced as a liquefaction potential map. That was back in the 1986. And it was used in areas in Japan that they were already under liquefaction in the past, and the data matched each other. But I personally refrain from that because I know that both the geotechnical engineers and the structural engineers want to be very punctual about liquefaction, and they prefer to do site assessments. So for me, this is a map that shows that when the earthquake happens, some areas are going to be more vulnerable than others. And so far, we have been confirming it every time we have an earthquake. And I will prove it to you why this is true in the next section. So bear with me for that. The results of the microzonation led us to create a strong motion network within the city. So what you see on the map is actually 7 stations that are operating right now within the limits of the city corp. And actually, the past 3 years has been expanded to a national strong motion network. So right now, we have 21 strong motion sensors recording acceleration in basically all over the country, and the plan is to expand it to at least double the size in the next 5 years. So we will have a database of events of different magnitudes available for anyone who is interested to use that data. One click back. So, just an example, we have done microzonation of Kingston in Jamaica. That was done back in 2018, where we also provided, from the microzonation, we provided the nerve classification for the whole Kingston metropolitan area. And tomorrow I'm going to show you an example of the risk that we calculated for Kingston. And the last example is from Rosso in Dominica, where we did the microzonation. Actually, it was a larger project where we microzoned several areas, but we also included the capital, Rosso, which we also then provided the nerve classification that you see on the map. So I'll take a break for now. If you have any questions. Yes, please.
So thanks for the presentation, which I think has highlighted a number of important aspects. You show the vulnerability map, which I think is very important for design purposes. Mm-hmm. And you mentioned that it's related to liquefaction. No. When it was first introduced to the world by publishing, yes, it was introduced as an index that it's a measured index that yes, if it exceeds a certain value, then the site is prone to liquefaction. Okay, but you know how the engineers identify and measure the liquefaction potential. It has very strict rules of how you're going to measure it and where it can happen or not. Okay. About, yes, solid yes. Index. Yes. So this doesn't follow any rule aside from measurements that you just use and you're like, okay, it's going to liquefy or it's not going to liquefy. When it was first introduced, it was introduced to an area that had already liquefied in Japan. Okay. So they went to the same area and they did the recordings and they said, okay, now we have an index of what is going to liquefy or not. I don't want to take that as granted, so for me, my interpretation is it's a vulnerability map. So the areas in red are going to be more vulnerable than the areas that are not in red. What is the index used for the vulnerability?
Oh, all right. Now I have to go a lot back. Can you please keep on going back? There. One more. One forward. All right. So you see on the right the images. All right. So this is a graph between the amplitude and the frequency. All right. And this has been graph is the curve is being produced by taking the spectral of the horizontal and divided by the spectral of the vertical. Right? Now, if we take the amplitude that the amplitude that you see here, and divide it by the square of the frequency, this produces an index. This is the KG index as it's been introduced to the world. So according to the publication, if this is above 20, then the site that is being produced, it's prone to liquefaction. So it is a measured factor. I personally don't want to say that the areas that you see there are going to liquefy.
Because my question was about, since if you go back to the map, please, of the vulnerability, because I think that it's very important for planning in a way, because you are showing that typically along the coast you have two seconds period, which is 0.5. So it means that all the coastal line it can be vulnerable, which is reasonable because it's close to the water.
Right.
But also, on the other hand, typically engineers are scared about potential of liquefaction, which is not always the case. Japanese has told us that liquefaction is also introducing a threshold acceleration, which means that you get an amplification, but because the soil is going to liquefy, then there is no amplification.
Right.
So have you, even through a first rule of thumb, evaluated this value of acceleration? Right. Just to check if the built asset, I'm a structural engineer, so I'm looking at the consequence on the built asset, if it's going to be vulnerable, or is it simply a geotechnical issue that then is going to affect only selective structure?
And that's why I avoided to use the word liquefaction.
Okay, understood. Understood now. Thank you.
And as I said, I will prove to you why this works once we finish with the questions.
Okay.
More importantly, where are we on that map? Yes.
Oh, you are in the red. You are dead in the red.
Okay. Okay, thank you. Anyway.
Good morning, everyone. Thanks for the presentation, Ilias. I wanted to ask, you saw so many information about the hazards that we might have, and you talk about Port of Spain, but are you doing something similar to other major cities like San Fernando, Orseguanas, and are you going to update the maps that we are using, or what is the plan for the future?
That's a good question. Actually, you should be happy to know that 2 out of the 4 Greeks who live in the country is in the room right now. Savas is a fellow Greek guy. Yeah, as I said in the beginning, we are doing 9 cities. So we started with Port of Spain, we did San Fernando, Diego Martin, South Tobago, Cuba, Saguanas, and right now we are in Saguanas and we'll continue to Arima and to the east-west corridor, more or less. So hopefully I'll do the whole country. The information, again, this is funded by Ministry of Planning and Development, so they are the benefactors of the whole thing. So they are to use them to update their planning plans. How we're going to update the maps that you are using, that is a good question, and I think that might steer a conversation between engineers and seismologists, how we can help you by what information we can provide to you so we can move forward. Okay, but as it stands right now, it is not really applicable to say we are going to update the maps that you are using by using this information. But this can serve as a guide for you of, okay, now we have this information, extra information about what's going on in a certain area. How can I use this to my benefit? Okay.
Very quick comment, if I can.
Yes.
Actually, the ministry is not here. This would be a very good plan for retrofitting.
Richard?
Because then you can plan what
I
to do
agree.
in the future.
I agree. All right, no questions. All right, so I'm going to give you a history lesson. Go ahead. Right. So once I produced the maps, I was curious why the result is such. So what I did is I locked myself in the libraries and I read every historical book and every historical map that I could find to be able to explain the map that actually stirred your interest. So we will start with Port of Spain under Spanish occupation. Now, under Spanish occupation, Port of Spain was a small village and the St. Anne River was to the west, not to the east. Its natural out to the sea was where today is Woodford Square. So Chacon, who was the last Spanish governor, actually blocked it and let the water come out from the dry river, which today is still the dry river. Okay? So this is the first reclamation that was done in Port of Spain. Next one. Now we are in the beginning of the 19th century, and the Port of Spain, now since the river has moved, can expand to the west. Nobody wants to go to the east up on the hill. So there is an expansion to the west. The governor at the time is Abercrombie. Next. Now we have a governor who stayed very briefly in the country. That's Sir Thomas Hislop, who continued the expansion of the village. It's still coming. It's still a small fishing village with not that much going on, but at the time, there is a fort in front of the city into the water that is protecting the city from whoever wants to attack. The fort was called Fort San Andres. Ever heard of it? Yeah. Do you know where it is?
Yeah, by the lighthouse.
Right. So, in the water.
You have to have an English
Now, in the 1820s, this young guy comes as the youngest governor and does a lot of things, actually. What he's doing is he's taking limestone from the quarries in Laventille, and he's throwing them in the water, reclaiming what today is the South Cape. So under his governorship, the Fort San Andres is not in the water. What he's also doing is that he created the botanical gardens. In order to water them, and next to them there were some cattle farms, he diverted the St. Anne's River to the west, so he will be able to water both the trees and to provide water for the animals. Now, today, the diversion is where the Wildflower Park is. So there used to be a river flowing over there. Next. Now, I found this map from a surveyor somewhere in the century, so I put it on today's context. So you can see how the development is going over there. Now the next one is a map that I found from some insurance company in Canada. So if I put it again on the today's context, you will see how we are developing, and you can see where the coast is compared to where we are today. Now, this is the first mayor of Port of Spain in 1938. That is Arthur Cipriani, who had the idea of the Deep Harbor project. So what he did was that the problem was that the large ships couldn't berth at Port of Spain because the seafloor is too shallow. So what he did is that he dug the floor to make it deeper so the ships can berth. And the material that he took out, he dumped it inside that red polygon you are seeing, reclaiming what today is, as we are sitting right now, and towards the sea, right? Now, the technique that they used for this was they brought in an Indian engineer to do that. So the technique that he used, that they were using back in India, it was to take the mangrove roots and then all this soft material that they dug from the seafloor, they putting it inside those mangrove roots, making it a basket, that they were drying it out, and then they were putting it inside that polygon you see in order to be able to reclaim the land. This is a picture, this is an aerial photograph from the Royal Air Force taken in 1940s, that if we put it on the map, one back please. Right, so if you see it, putting it on the map, you see how the coast starts looking more and more like today. The next one is from the US Air Force, taken in the, can you remember? In the 60s. Again, putting it on the map, it will produce you more or less what we have today. After that, the only reclamation that I found out was the Invaders Bay, where Movie Town is today. That I don't have any evidence, I just found it on Google. And if you add all that, you will end up with this. So that explains why I don't want to call it liquefaction, and I want to call it vulnerability. Okay? Any further questions? All right, so thank you very much.
Thank you.